Hello, welcome to our demonstration of sentiment analysis using Amazon reviews. The major objective of our project was to implement a very scalable solution so that we could process millions of text records efficiently. And for this purpose, we used PySpark and Python.
Well, now coming to the data characteristics, we have total of 4 million samples in data, which is divided into training sets and a testing set. Training set is of 3.6 million, which both the data training sets and the test sets is balanced, which is 1.8 million each for the training set classes and the test set for 200K each classes. We have three features, which is first is polarity level, which is the sentiment analysis, which has been classified between negative and positive. We have the reviews star, which is less than three, or three is marked as negative, and four and five is marked as positive. We have title and the review. Our analysis shows that the positive reviews are shorter than the negative one. Titles are consistent to brief across both sentiments with around 24 characters. Text length vary ranging from 21 to 913 characters, which suggests that the content is authentic and user generated. Well, coming to the data pre-processing pipeline, our pipeline consists of four major stages. We start with our massive data set of 3.6 million training reviews. The first transformation is the text pre-processing, where we perform systematic cleaning through four critical steps: the stop word removal, URL removal, email address removal, and tokenization. This standardization was essential for consistent model performance. Next, we moved to feature engineering, where we implemented TF-IDF factorization with carefully tuned parameters, a minimum document frequency of 5 to filter out rare terms, and a vocabulary size of 3000 to manage computational complexities. We then used chi-square selection identify the 1000 most significant feature, dramatically reducing our feature space while maintaining predictive power. Then we have this model implementation architecture. Our implementation architecture showcased the robust cross-validation framework we built for each model. Logistic regression, naive Bayes, and random forest went through this pipeline. What particularly interesting here is how we handle model validation. For logistic regression, we explore regularization parameters between 0.01 and zero point 0.1 and elastic net parameters from 0 to 0.5. This helped us find the sweet spot between model complexities and performance. We then implemented threefold cross-validation across all models with a fixed seed of 42 for reproducibility. The evaluation was standardized using the area under ROC curve and our primary metrics, allowing fair comparison across model. A key design decision was using the binary classification evaluator for consistent evaluation across all three models, despite their different underlying algorithms. This standardization was crucial for our comparative analysis. What's not immediately visible in this diagram, but worth noting, is that this entire pipeline was implemented using PySpark ML pipeline API, ensuring scalability and consistent processing across our distributed computing environment.
For our evaluation, we used a multimetric performance assessment. We used area under the ROC curve, accuracy, precision, recall, F1 score, etc. And for error analysis, we looked at the confusion matrix and a detailed classification of false positive and false negatives. When we move on to the results, we can see interesting insights. The logistic regression achieved highest area under the curve score of 0.91, which shows its excellent ability to distinguish between positive and negative sentiments. This shows that it's very good at handling the nuanced language in customer reviews. Naive Bayes surprised with the highest F1 score of 0.84, despite it being the simplest model amongst all three. What is very interesting is its training time. If you look at the lower graph, it's roughly 3 times faster than both logistic regression and random forest. This efficiency performance balance makes it an attractive choice for rapid deployment scenarios. The random forest model showed strong precision but lower recall, which means that it was more conservative in its positive predictions. This can be valuable in situations where false positives are more costlier than false negatives. A key insight from our error analysis revealed that all models struggled with complex linguistic patterns. For example, naive Bayes had difficulty with negations like not ultimate, not expected, etc., while logistic regression was better at handling these nuanced expressions. The practical implications of these findings are very significant. For real time sentiment analysis, where speed is crucial, naive Bayes would offer the best balance of performance and efficiency. However, for applications which require more nuanced understanding of sentiment, logistic regression's superior area under the curve ROC score makes it the better choice. To conclude, while each model has its strength, the choice between them should be guided by specific user case requirements. Thank you.